Welcome to the class. Today we are going to discuss about peak inverse voltage. What is the meaning of a peak inverse voltage? Then we are going to discuss about the zener diode and the characteristics of zener diode. Now let us begin with a peak inverse voltage. In a semiconductor diodes, peak reverse voltage or a peak inverse voltage is the maximum voltage that a diode can withstand in the reverse direction without breaking down. If this voltage exceeds, the diode may be destroyed. It means that up to this voltage, the diode blocks conduction of current in the reverse direction. Hence, the peak inverse voltage of a diode in the bridge rectifier is equal to the peak value of supply voltage. So suppose consider this circuit where the diode is connected or diodes are connected to the output of a transformer. If I consider this is the half wave rectifier, that is the half of the circuit, that is this part, where only one diode is connected to the output of a transformer, so we can call it as a half wave rectifier. And if I connect diodes to the output of the transformer where the center is tapped to the ground, so this is called the full wave rectifier. So here you can see here, this is the voltage which is applied. So once it reaches to the maximum, to this, so the positive half will come across the diode D1. At the same time, the negative maximum will come across D2, so the output is a rectified one. As usually, a PN junction or a diode is used as a rectifier. It is used to convert AC to DC. Therefore, care should be taken that during the negative half cycle, the peak value of AC voltage should not be more than the rated value of the peak inverse voltage of the diode. So now next we can go for a ripple factor. The output of a rectifier consists of a DC component and an AC component. This AC component is undesirable and cause for the pulsating in the rectifier output. So the AC component present in the pulsating output, that is in the rectifier output, is known as ripple. The ratio of RMS value of AC component to the DC component in the rectifier output is known as ripple factor. That is, ripple factor is nothing but RMS value of AC component present in rectifier output by average value of rectifier output. So ripple factor is very important in deciding the effectiveness of a rectifier. The smaller this component, the more effective is the rectifier. The ripple factor of a half wave rectifier is 1.21 and the ripple factor for the full wave rectifier is 0.483. The ripple can be reduced by smoothing capacitors, which converts the ripple voltage into a smoother DC voltage. For this, aluminum electrolytic capacitors are widely used and have the capacitance of 100 microfarad or more. Now let us go for some basic concept of the zener diode. The zener diode is a special type of a diode designed to allow the current to flow backwards when the certain set of reverse voltage known as zener voltage is reached. A zener diode is a silicon semiconductor device that permits current to flow in either a forward or a reverse direction. The diode consists of a special heavily doped PN junction designed to conduct in the reverse direction when a certain specified voltage is reached. Ordinary diodes are forward biased. You remember this? Ordinary diodes are reverse biased and work in the forward direction. They have a large forward current flowing through them with a negligible voltage drop across them. If you operate an ordinary diode in the reverse biased, it conducts insignificant current until the voltage applied across them exceeds the reverse breakdown voltage. Once that happens, large current flow through the junction and the diode may get destroyed. The zener diode is a particular type of a diode that solves this problem. So here the zener diode is a particular type of a diode that solves particularly this problem when the applied voltage exceeds the reverse breakdown voltage. The zener diode is a particular type here. We operate a zener diode in a reverse bias condition, and this diode does not get damaged even when the voltage across this exceeds the reverse breakdown voltage. Let us learn about this, what is the zener diode, how it is going to work. Zener diodes are heavily doped than ordinary diodes. They have extra thin depletion layer. When we apply a voltage more than the zener breakdown voltage, that is the range from 1.2 volt to 200 volts, the depletion region vanishes and the large current starts to flow through the junction. There is a crucial difference between the ordinary diode and a zener diode. Now this is the characteristics of a zener diode. A graph of current through versus the voltage across the device is called the characteristics of a zener diode. The first quadrant is this is the first quadrant. The first quadrant is the forward biased region. Here the zener diode acts like an ordinary diode. When the forward voltage is applied, current through it, but due to the higher doping concentration or a higher current flows through the zener diode. In the third quadrant, here the graph shows the current versus voltage curve when we apply the reverse bias to the diode. That is this quadrant. Here the diagram you have Z that refers to a zener breakdown voltage. Until the voltage reaches zener breakdown level, tiny amount of current flows through the diode. Once the reverse bias voltage becomes more than a zener breakdown voltage, a significant amount of current starts flowing through the diode. Due to the zener breakdown, the voltage remains at a zener breakdown voltage value, but the current through the diode reverses when the input voltage gets increased. Due to the unique property of a zener diode, the depletion region regains its original position when the reverse voltage gets removed. This zener diode doesn't get damaged despite this massive amount of current flowing through it. This unique functionality makes it very useful for many applications. Now some applications of zener diode. Zener diodes are usually used for the voltage regulation as references elements, surge suppressors, and in switching applications and clipper circuit. So this is the voltage regulator circuit where zener is connected. Zener is connected in series to the RS. So this is a symbol of a zener diode. The load voltage equals breakdown voltage V of Z of the diode. Here, the series resistor limits the current through the diode and drops the excess voltage when the diode is conducting. Resistor RS is connected in series with a zener diode to limit the current flow through the diode with voltage source. So here you can see resistor R of S, that is this resistor, is connected in series to the zener diode to limit the current flow through the diode with a voltage across voltage source. V of S being the connected across the combination. The stabilized output voltage V out is taken out from the zener diode. So here this is nothing but the stabilized output voltage. The zener diode is connected with its cathode terminal connected to the positive of the DC supply, so it is reverse biased. We will be operating in its breakdown condition. Resistor RS is selected so that to limit the maximum current flowing through it. With no load connected to the circuit, the load current will be 0 and all the circuit current passing through the zener diode will in turn dissipates its maximum power. Also, a small value of a resistor RS will result in greater diode current when the load current is connected. This will increase the power dissipation requirements of the diode, so care must be taken when selecting the appropriate value of a series resistance, and so that the zener's maximum power rating is not exceeded under this no load or a high impedance condition. The load is connected in parallel with the zener diode, so the voltage across R of L is always the same as the zener voltage. There is a minimum zener current for which the stabilization of a voltage is effective, and the zener current must stay above all the value operating under load within its breakdown region at all times. The upper limit of the current is, of course, dependent upon the power rating of the device. The supply voltage V of S must be greater than V of Z. One small problem with the zener diode is to stabilize the circuit is that the diode can sometimes generate electric noise on top of the DC supply as it tries to stabilize the voltage. Normally, this is not the problem for the most applications, but the addition of a large value decoupling capacitors across the zener's output may be required to give the additional smoothing. So the zener diode is always operated in the reverse bias condition. As such, a simple voltage regulator circuit can be designed using a zener diode to maintain a constant DC output voltage across the load in spite of variations in the input voltage or changes in the load current. Zener diode regulator consists of a current limiting resistor RS connected in series with the input voltage V of S, with the zener diode connected in parallel with the load RL in this reverse biased condition. The stabilized output voltage is always selected to be the same as the breakdown voltage.